What specific problem does the proposed Logit Calibration, LoCa method aim to solve, and why is it significant in the context of knowledge distillation?
The proposed Logit Calibration, LoCa method aims to solve the problem of misinstruction in knowledge distillation, where a student model is misled by incorrect logits from an inexperienced teacher model. This misinstruction occurs when the teacher's predictions do not align with the true labels, leading to erroneous learning for the student model. The significance of addressing this issue lies in the need to maintain valuable dark knowledge, such as class discriminability, while ensuring that the logits are consistent with the ground truth labels. By calibrating the logits, LoCa effectively prevents the student from being misled, thereby enhancing the overall performance of the knowledge distillation process. Experimental results demonstrate that LoCa significantly improves the accuracy of the student models across various tasks, highlighting its effectiveness in mitigating the detrimental effects of misinstruction.
How does the proposed method or algorithm, LoCa, work? Illustrate the calibration process step by step, including any mathematical formulations involved.
The proposed Logit Calibration, LoCa method works by addressing the misinstruction issue in knowledge distillation while preserving valuable dark knowledge from the teacher model. The calibration process is modeled as an optimization problem with three main goals: ensuring the teacher logits are consistent with the ground truth label, maintaining the ratio of non-target logits, and satisfying the probability distribution constraint. 1. Prediction correctness. The calibrated logit for the ground truth label, GT, is set to be the maximum among the logits, ensuring that the prediction aligns with the true label. This is mathematically represented as P_GT LoCa equals max P. 2. Non-target proportion invariance. The method preserves the ratios between non-target logits, ensuring that the dark knowledge is retained. This is achieved by maintaining the proportions of logits for non-target classes during calibration. 3. Probability distribution. The calibrated logits must satisfy the constraint that the sum of probabilities equals 1, formulated as sum_I equals 1 C, P_I LoCa equals 1. By introducing a scaling factor, S equals alpha C dot sigma, where alpha is a hyperparameter, LoCa adjusts the logits accordingly, ensuring that the calibration process meets the aforementioned constraints while effectively mitigating misinstruction. This structured approach allows LoCa to enhance the performance of the student model during knowledge distillation.
Can you provide a simple yet illustrative example to demonstrate how LoCa calibrates logits? Walk through the main algorithm steps using this example.
To illustrate how the Logit Calibration, LoCa method calibrates logits, consider a scenario where a teacher model incorrectly predicts an image of a cat as a dog. In this case, the teacher's logits indicate dog as the highest probability class, leading to misinstruction for the student model. The first step in LoCa is to ensure that the calibrated logits align with the ground truth label, which is cat, thus correcting the misinstruction. This is achieved by introducing a scaling factor that adjusts the logits while maintaining the ratio of non-target logits, preserving valuable dark knowledge. Specifically, LoCa sets the logit for the ground truth class to be the maximum among the logits, while scaling the other logits accordingly to ensure that the sum of probabilities remains 1, thus effectively calibrating the logits to avoid misinstruction while retaining useful information.
What are the theoretical and practical benefits of using the LoCa method over traditional knowledge distillation techniques like vanilla KD?
Theoretical benefits of the LoCa method include addressing the misinstruction issue, which occurs when teacher logits indicate incorrect class labels, leading to optimization conflicts during knowledge distillation. By ensuring that the calibrated logits are consistent with the ground truth labels, while preserving the ratios of non-target logits, LoCa effectively maintains valuable dark knowledge that traditional methods might discard. Practically, LoCa demonstrates significant performance improvements over vanilla KD in both image classification tasks, e.g., achieving A0, 42% increase in accuracy on CIFAR 100 and text generation tasks, as evidenced by consistent enhancements across various datasets. Additionally, LoCa exhibits robustness across different model architectures and hyperparameters, showing stable performance improvements, particularly with an alpha range of 0.9 to 1.0. Overall, LoCa not only enhances the accuracy of the student model, but also reduces the risk of misguidance during the distillation process, making it a superior alternative to traditional KD techniques.
How is the effectiveness of the LoCa method validated? Discuss the datasets, benchmarks, and performance metrics used during experiments.
The effectiveness of the LoCa method is validated through extensive experiments on two primary tasks: image classification and text generation. For image classification, datasets used include CIFAR 100, which contains 50,000 training images across 100 categories, and ImageNet, a larger dataset with 1.28 million training images across 1,000 classes. The performance metrics for these tasks are based on validation accuracy, where LoCa consistently outperformed the baseline vanilla KD method, achieving improvements of 0.42% on CIFAR 100 and 0.49% on ImageNet for top 1 accuracy. In text generation, the LoCa method was evaluated on the DALI, SNI, and UNI datasets, with performance measured using average Rouge-L scores. The results demonstrated significant improvements over both standard fine-tuning and KD methods, with statistical significance indicated by p-values less than 0.001, confirming the robustness and effectiveness of the LoCa approach across various benchmarks.
What limitations or challenges are associated with the LoCa approach, especially concerning model generalizability or computational overhead?
The LoCa approach faces certain limitations, particularly regarding model generalizability and computational overhead. While LoCa demonstrates consistent improvements across various datasets, the performance on ImageNet is more sensitive to the hyperparameter alpha compared to CIFAR 100, indicating that adjustments must be moderate to avoid degrading performance. Additionally, when alpha is set to 1 or greater, the predicted labels may not align with the ground truth, leading to worse performance than the baseline vanilla KD, highlighting a challenge in maintaining prediction correctness. In terms of computational overhead, although LoCa incurs only a minor increase in timing, less than 1% additional time per epoch, this could still be a concern in resource-constrained environments where efficiency is critical. Overall, while LoCa effectively addresses MIS instruction, its sensitivity to hyperparameters and slight computational costs may limit its applicability in certain scenarios.